Welcome to this comprehensive guide on debugging services and connectivity issues in Kubernetes. Service connectivity problems are among the most common challenges when working with Kubernetes clusters. Throughout this tutorial, you'll master the essential techniques for diagnosing service discovery failures and networking problems. By the end, you'll have a systematic approach to troubleshoot any service-related connectivity issue with confidence. Let's start by understanding the four most common service connectivity problems you'll encounter. First, connection refused errors occur when service endpoints are unreachable or pods aren't in a ready state. Second, DNS resolution failures happen when a service name doesn't properly resolve to its cluster IP address. Third, network policy blocks can deny traffic through misconfigured ingress or egress rules. Finally, port mismatch issues arise when the service port doesn't align with the actual container port. Recognizing these patterns is the first step toward effective troubleshooting. Before diving into debugging, let's review how service discovery works in Kubernetes. DNS-based discovery is the primary mechanism where every service automatically receives DNS records in the format service name .namespace.svc.cluster.local. The cluster IP assignment provides a stable virtual IP address that intelligently load balances traffic across multiple pod endpoints. Endpoint management continuously tracks the IP addresses of ready pods that match the service's selector labels. Understanding these three components is crucial because most connectivity issues stem from problems in one of these areas. Now let's establish a systematic debugging workflow. Step 1. Verify the service configuration by checking that the service exists and has the correct selector labels. Step 2. Validate endpoints to ensure pods are being selected and are in a ready state. Step 3. Test DNS resolution to confirm the service name properly resolves to the cluster IP. Step 4. Check network policies to verify that traffic is allowed between pods and services. Following this methodical approach ensures you don't miss any critical component and helps you quickly isolate the root cause of connectivity issues. The first diagnostic command is kubectl get services in the target namespace. This command provides essential information at a glance. Verify that the cluster IP shows a valid IP address has been assigned to the service. Check the port mappings in the PORTS column to confirm they match your application requirements. Validate that the service type is appropriate for your use case, whether it's cluster IP, node port, or load balancer. Also, pay attention to the service age, as recently created services might indicate recent configuration changes that could be causing issues. For deeper inspection, use kubectl describe service followed by the service name and namespace. This command reveals three critical pieces of information. First, examine the selector labels section, as these must match your pod labels exactly for endpoint selection to work. Second, verify the port configuration including the port, target port, and node port settings to ensure they align with your application. Third, review the events section at the bottom for any warnings or errors that occurred during service creation. Mismatch selectors are one of the most common causes of service connectivity failures. The next crucial step is checking endpoints with kubectl get endpoints followed by the service name and namespace. This reveals whether your service is actually selecting any pods. If endpoints are present, you'll see the IP address and port combinations of ready pods that match your service selector. If no endpoints appear, this indicates either a selector mismatch or no pods are in a ready state. To diagnose selector issues, compare the service selector labels with the actual pod labels. Also verify that pod readiness probes are passing, as only ready pods become service endpoints. DNS problems are another frequent cause of connectivity issues. To test DNS resolution, run a temporary debug pod using kubectl run test-DNS with the BusyBox image. From inside this pod, use nslookup to query the full service name in the format service name .namespace.svc.cluster.local. If DNS is working correctly, it should return the service cluster IP address. If DNS resolution fails, The problem likely lies with the core DNS pods in the Kube system namespace. Check that core DNS pods are running and healthy. Network policies can silently block traffic if not configured correctly. Use kubectl get network policies in your namespace to list all policies. Check the ingress rules to verify that incoming traffic is allowed to your service pods. Review the egress rules to ensure outgoing traffic is permitted from client pods. Remember that network policies follow a default deny model, meaning if a policy exists but doesn't explicitly allow traffic, that traffic will be blocked. Empty or incomplete policies are a common culprit in connectivity issues. Port and protocol mismatches are subtle but critical issues. Understanding port mapping is essential. The port is what the service exposes, while the target port is the actual container port, and these must match exactly. Protocol matching matters too, as TCP and UDP are distinct protocols, and both the service and pod must agree on which one to use. The default protocol is TCP. To test connectivity, use tools like curl or telnet from another pod to verify you can reach the service and receive proper responses. Named ports can reduce configuration errors by using consistent names instead of numbers throughout your pod and service specifications. Let's review the most common pitfalls and their solutions. Selector label typos or mismatches are easily fixed by double-checking labels using kubectl get pods with the show labels flag. When pods fail readiness probes, either fix the underlying application health issue or adjust the probe timing and threshold settings. Using the wrong namespace is surprisingly common, so always use the namespace flag or set your context namespace appropriately. If a service was created before the deployment, don't worry. Endpoints automatically update once pods become ready, so this typically resolves itself. Let's wrap up with a quick reference checklist for debugging service connectivity. First, confirm the service exists and has a cluster IP assigned. Second, verify selector labels match pod labels exactly. Third, check that endpoints show ready pod IP addresses. Fourth, test that DNS resolves the service name correctly. Fifth, ensure port and target port are configured correctly. Sixth, confirm the protocol matches between service and pods. Seventh, verify network policies allow the required traffic. Finally, validate that pods are passing their readiness probes. Use this checklist whenever you encounter service connectivity issues, and you'll systematically identify and resolve problems. You've now mastered service connectivity debugging in Kubernetes.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.